Hey there, everybody. Welcome back. We are in 13.4 in Anton's 11th edition for Calculus 3. We are looking at the differentiability and continuity of multivariable functions. We'll also take a look at total differentials we talked about in the last video. So the theorem I told you that was going to make this all a lot easier, and it's proved in higher order math classes at like a university if you go into real analysis and all that good stuff like that. If all the first order derivatives of a function exist and they are continuous at a point, then the function is differentiable and continuous at that point. That's a great trait. All we need is the first order derivatives to exist and be continuous there. And then our overall function is differentiable and continuous. So let's take a look at an example. We've got f of xy equals x squared plus y squared plus 2xy. So let's take a look at our partial derivatives. F of x equals 2x plus 2y. Not f of x. The partial derivative of f with respect to x is 2x plus 2y. The partial derivative of f with respect to y is 2y plus 2x. Remember, when you're taking partials, you hold the other variables constant. They both exist, and since they're polynomial functions, they're continuous everywhere. So f of xy is differentiable and continuous everywhere for this function. Okay. I said we talk about total differentials. In two space, we have df or dz. We take the partial with respect to each component, evaluate it at x naught, y naught, or the whatever point we're looking at. And then whatever partial we took the derivative with respect to, we multiply it by that d component. So I've got partial of f with respect to x at x naught, y naught times dx, plus partial of f with respect to y at x naught, y naught dy. That's in two space. We scale it up to three space, df or dw, if we want to call w x, y, z. We've got the partial of f with respect to x at x naught, y naught, z naught times dx, plus the partial of f with respect to y at x naught, y naught, z naught, dy, plus the partial with respect to z at x naught, y naught, z naught, dz. And since delta f minus our total differential is a lot less than the actual distance that we're looking at, we can use this to approximate delta f using df. So let's take a look at that. Let's approximate delta f using df. I've got a function here, f of xy, which is z, equal, we're going to use that x squared plus y squared plus 2xy. We want to approximate the change in z. If we're going from 3.1 to 2.97 and 1.04, so dz, we did dy, we did in the last clip there, we found the partial with respect to x and the partial with respect to y. 2x plus 2y dx and 2y plus 2x dy. So what we want to do, and let's take a look at what's going on here. Dx is we're got to change from 2.97 and 1.04 is what we're trying to approximate using 3.1. Because 3.1 is a lot easier to plug in. I can do this plugging it in and figure it out without looking at it. 3 squared is not 9 plus 1 plus 2 times 3 plus times 1 is 16. Z is 16. I can't do the same thing with 2.97, 1.04. But we want to approximate it using this thing. So notice our dx, our change in x, 2.97 to 3 is negative 0.03. And dy is, our delta y is 1.04 minus 1 is 0.04. We're going to plug in everything we have here. We're approximating 2.97, 1.04 at 3.1. So we're evaluating dz at 3.1. Okay? And so our delta z is approximately that dz. We're just plugging the things in. X is 3, Y is 1, and dx is negative 0.03. You plug them all in, you do the calculations on them, you get 0.08. And you will find that if you actually do find delta Z, or do f of 2.97, 1.04 minus f of 3, 1, you're going to find it's 0.0801. So this is a good approximation, and it was pretty easy to do. Yeah, you're going to be using a calculator for this, and a lot of times you are for a lot of things, but it's good to be able to approximate stuff with a nice, simple method. That'll be it for this video. Peace.